Good morning children, welcome back to the chemistry session. In previous session we have seen Bohr's explanation of line spectrum of hydrogen atom and Bohr's limitation. In today's session we are going to talk about towards quantum mechanical model of an atom. There are some theories who had given basic idea of quantum mechanics. Let us start today's session children. Towards quantum mechanical model. So there are two theories. Those had given idea about the quantum mechanical model of an atom. They are, one is dual nature of matter, dual nature of matter, and second theory Heisenberg's uncertainty principle. One is dual nature of matter and second theory Heisenberg uncertainty principle. These two theories we are going to discuss in today's section. So let us start today's section. First one, let's see first theory, dual nature of matter. This dual nature of matter was explained by or was proposed by de Broglie. So de Broglie stated that when electrons are radiation in motion, they possess both particle and wave nature, known as dual nature. Similarly, matter when in motion also possess particle nature and wave nature. I am repeating children. De Broglie stated that when electrons in motion or when radiation in motion, it possesses both particle nature and wave nature, that is called dual nature of matter. Likewise, when matter is in motion, it also possesses both particle nature as well as wave nature, that is called dual nature of matter. And de Broglie also derived an expression for dual nature of matter. For that, he considered two theories. One is Planck's quantum theory. Planck's quantum theory is equal to h nu. Let us consider question 1. Here is energy of radiation is directly proportional to frequency of emitted radiation. Here h is Planck's constant. And second one, Einstein's mass energy equivalence. Einstein's mass energy equivalence. That is equal to mc square. Let's consider equation 2. According to Einstein, mass of photon is directly proportional to the square of velocity of light and its mass. He equated both of the equations because these two related to the energy of the radiation. So that he equated both the equations. On equating both the equations, we get h nu is equal to mc square. We know that mu is equal to c by lambda. Frequency of radiation is inversely proportional to turbulence. Substitute mu h into c by lambda is equal to mc square. What we want? We want lambda value because we want to find out wavelength of the radiation. So lambda is equal to hc by mc square. Here square and c get cancelled. What is the present here? Lambda is equal to h by mc. So lambda is equal to h by mc. The lambda is wavelength of the radiation and h is Planck's constant. M is mass of the particle. C is velocity of the particle, that is velocity of the light. It can be written as h by p. So lambda is equal to h by p, children. Where lambda is wavelength of the radiation, h is Planck's constant, p is momentum. P is momentum, children. That means when the radiation has high wavelength, when the wavelength of the radiation is more, its momentum is less because they are inversely proportional to each other. So lambda is inversely proportional to P means if the wavelength of the radiation increases, its momentum is decreases. Momentum is nothing but it is the product of mass and velocity. Here velocity of the light is equal to velocity of the frequency of the radiation. It can be written as lambda is equal to h by mv also. Because we assume that light is made up of particle. Similarly, matter is also possess dual nature. So when the radiation of the wavelength is inversely proportional to its momentum, and we consider that de Broglie considered that the matter has dual nature. That means it possesses both particle nature as well as wave nature. When the matter has wave nature, it possesses the properties like diffraction. Diffraction is one of the phenomena of light, one of the property of light. That's why the diffraction phenomena is useful in development of electron microscope, children, because they consider matter as dual nature, like electron or radiation in motion. That's why lambda is inversely proportional to momentum. So lambda is equal to h by p. If the mass of the particle increases, its wavelength value is decreases. That's why for microscopic objects, its wavelength value is maximum. Microscopic objects like subatomic particles like electron, proton and neutron, those are microscopic particles. They possess high wavelength values because they have less mass. For microscopic objects, its wavelength values are much. For macroscopic objects, that means if the mass of the object is more, its wavelength values are decreases. That's why it mostly applicable to microscopic objects are subatomic particles like electron and proton. And this is the relation between, this is de Broglie hypothesis, children. So lambda is equal to h by mv. So let us represent this de Broglie hypothesis in terms of kinetic energy, children. We know that kinetic energy K is equal to other forms of de Broglie hypothesis, de Broglie expression. Kinetic energy K is equal to half mv square. Then 2Ke is equal to mv square. Then 2Ke into m. So under root 2, V is equal to under root 2Ke by m. Not 2Ke, children. V is equal to 2Ke under root 2. Here V is equal to 2 ke by m under root 2. Substitute the V value here. Lambda expression, lambda is equal to h by m into V value under root 2 k e. So it is in denominator, it will go to numerator, root over m. Here m can be written as root m into root m. So here 1 root m gets an answer. So it can be written as lambda is equal to h by root over 2 k e into m. This is the other form of de Broglie expression. In terms of kinetic energy, lambda is equal to h by root over 2 k e into m. Where lambda is wavelength of the radiation, h is Planck's constant, k is kinetic energy of the radiation, m is mass of the particle. This is called de Broglie hypothesis or dual nature of matter. We consider de Broglie hypothesis states that when electron in motion has dual nature. Similarly, when matter is in motion has both particle nature and wave nature is called as de Broglie's hypothesis. Next. Let us see Heisenberg's uncertainty principle. We will have the problems based on these two theories children. Dual nature of matter and Heisenberg's uncertainty principle. And second theory is Heisenberg's uncertainty principle. This Heisenberg's uncertainty principle states that it is impossible to simultaneously measure the exact position and the exact momentum of an electron at a given instant. I am repeating children. Heisenberg's uncertainty principle states that it is impossible to simultaneously measure the exact position and the exact momentum of an electron at a given instant. The mathematical expression of Heisenberg's uncertainty principle is delta x into delta v is greater than or equal to h by 4 pi. It's the mathematical expression of Heisenberg's uncertainty principle. What is the terms delta x and delta p here? Delta x means uncertainty in position. Delta v means uncertainty in momentum. I am repeating children. Delta x means uncertainty. What do you mean by uncertainty? Uncertainty means not accurate. Uncertainty in position. Delta p means uncertainty in momentum, which is more than that of or greater than or equal to h by 4 pi. Here delta p also can be written as delta x into m into delta v, because we know that momentum is mass into velocity. P is equal to mv. We have seen before. P is equal to mv. So delta x into m into delta v greater than or equal to h by 4 pi. That is equal to delta x into delta v greater than or equal to h by 4 pi m. This is the expression of Heisenberg's uncertainty principle. It states that delta x means it is not possible to measure simultaneously the exact position and exact momentum of an electron at a given instant, because according to Niels Bohr theory, Bohr considered that electron is about circular paths. That means electron revolving around the nucleus in a circular orbits of fixed energy and radius. And he considered that electron as a material particle. When the electron is revolving in the circular orbits, we can exactly find the position and velocity of the electron when the electron is revolving in these stationary orbits. But according to uncertainty principle, it is impossible to measure simultaneously the exact position and exact momentum of an electron at a given instant. Suppose it is an unlabeled line. So we want to find out the length of the line. Suppose if you want to find out the length of the line, if you want to measure this line, how can you measure this line? It's unlabeled line. By using some device, we measure the line like some labeled scale. Can we measure the length of the line using meter scale? No, it's not possible. By meter scale, we cannot measure the length of the line. By using millimeter scale, we can accurately measure the length of the line. By centimeter scale, we can measure length of the line, but may not accurately. By using millimeter scale, we can accurately measure the length of this unlabeled line. Similarly, if we want to find out the position of the electron in circular paths, then we have to use the radiation of least wavelength. When the radiation of least wavelength possesses high momentum, because the relation between wavelength and momentum is, we discussed it before, that lambda is equal to h by p. So lambda is inversely proportional to p from dual nature matter or from de Broglie hypothesis. When the radiation has least wavelength, then its momentum is maximum. When high momentum radiation strike the electron, because we wanted to find out the position and velocity of the electron in circular paths. For that, we have to use wavelength of least wavelength. But wavelength of least wavelength has high momentum. When this high momentum radiation incident on the electron, then this high momentum radiation hit the electron. Then collision happen between the electron and this high energy radiation. That's why we can able to find out the position of the electron in the circular orbits, but it is not possible to find out the velocity of the electron at a given instant, because we wanted to see the position of electron, because electron is a microscopic object. If you want to see the position as well as velocity of the electron at a given point, it is not possible. That is given by Heisenberg's uncertainty principle. So that is called, where delta x is uncertainty in position, where delta v is uncertainty in velocity. Here, if delta x value is minimum, that means uncertainty of the electron is minimum. That means if we know the exact position of electron with high accuracy, then delta x value is minimum. When delta x value is minimum, what about delta v value? Delta v value would be maximum. This is because here delta x, here if it comes this side, it will be denominator. That's why if delta x value increases means uncertainty in position of electron. If uncertainty in position of electron, that means we are unable to find out the position of the electron or location of the electron. That means its velocity is maximum. Its uncertainty velocity is maximum. That's why delta x value increases. That means uncertainty of electron is maximum. Its delta v, uncertainty in velocity is increases. On the other hand, delta v means uncertainty of electron is increases, then delta x value, uncertainty in location of electron, gets decreases, and vice versa. So this is called Heisenberg uncertainty principle. So this states that it is impossible to measure simultaneously the exact position and momentum of an electron at a given instant. This is called Heisenberg uncertainty principle, and it's the expression of Heisenberg's uncertainty principle. Let us talk about significance. Significance of Heisenberg uncertainty principle. We discussed just that trajectory of an electron. Trajectory of an electron in a circular path. Because according to Bohr's atomic model, electron is a material particle. So we consider that electron moving around the nucleus in stationary orbits. And he explained that in stationary orbits we can calculate position as well as velocity of an electron accurately. But according to Heisenberg's uncertainty principle, it is impossible because trajectory of any object depends on its velocity and its position in the given path. But in case of subatomic particles or microscopic objects, we have to use high momentum radiation. When high momentum radiation strikes the electron or subatomic particle, the position we can calculate, we can identify location, it's possible, but its velocity is not possible at an instant. So trajectory of an electron could not be explained by Bohr's atomic model. And second one, this Heisenberg's uncertainty principle only applicable to microscopic objects. It's only applicable to microscopic objects. Microscopic objects need subatomic particles like electron, proton, because electron charge is minus 1.6 into 10 to the power of minus 9 coulombs, and its mass is 9.1 into 10 to the power of minus 31 kg. Its mass is very less. So let us apply uncertainty principle here. Delta x into delta v is equal to h by 4 pi m. The h value 6.62 into 10 to the power of minus 34 joule/second, and pi 4 into pi 3.14, and mass of electron is 9.1 into 10 to the power of minus 31 kg, 10 to the power of minus 4, 10 to the power of minus 4 seconds. So for microscopic objects, this uncertainty value is maximum. Uncertainty value is maximum for microscopic objects. But in case of macroscopic objects, let us say mass value is 10 to the power of minus 3 kg. Let us consider 10 to the power of minus 3 kg of an object. We want to find out uncertainty in microscopic objects. Then use the relation delta x and delta v is equal to 6.62 into 10 to the power of minus 34 by 4 into 3.14 into mass value 10 to the power of minus 3 kg. If we simplify this, we will get some value. So, in that case, this uncertainty position and uncertainty velocity is minimum. And your delta x and delta v is minimum. When the value is minimum, uncertainty is less. For microscopic objects, this uncertainty position and velocity is maximum. That is the reason why it is impossible to measure simultaneously exact position and exact momentum of an electron at a given instant in circular orbits. That's why Bohr's theory had failed according to the Heisenberg's uncertainty principle. So these two theories, dual nature of matter and Heisenberg's uncertainty principle, had given idea of quantum mechanical model of an atom. So according to quantum mechanical model of an atom, they replace the terms like uncertainty in position as well as momentum. They propose the word probability of an electron in the space. So that is the basis of quantum mechanical model of an atom. The basis of quantum mechanical model of an atom is on the basis of dual nature of matter and Heisenberg's uncertainty principle. So according to Heisenberg's uncertainty principle, for macroscopic objects, uncertainty in position and velocity minimum. For microscopic objects, its uncertainty is maximum. So these two theories are the origin of quantum mechanical model of an atom. So in quantum mechanical model of an atom, they replace the terms by probability of an electron in the space. So this is today's section, children. In today's section, we have seen towards quantum mechanical model of an atom, that is de Broglie hypothesis, that is dual nature of matter, and Heisenberg's uncertainty principle. This is today's section. I hope you understand today's section, children. We'll meet in next section. Thank you.